Hello there! How do vision transformers work? This is what I have been asking myself lately too. We're already tired of hearing news about vision transformers being state of the art here and there and everywhere. Everywhere in computer vision means ImageNet. But we have also come to see vision transformers with convolutional biases in them, like the hierarchical swing transformer, which has a limited attention window, and we started to get some mixed feelings about what works best. Is it now convolutions or is it multi-head self-attention? In the last video, we got entirely confused about who wins the fight between ConvNets and transformers. We saw with ConvNext how a modernized ConvNet can compete with transformers. So it's time to read and explain this paper that brings more insight into what makes vision transformers so special. Multi-head self-attention. And why they are maybe not as special as we think, or not for the reasons we originally had in mind. Oh, here's my alert that we should thank Weights and Biases for supporting us for this video. Today we want to highlight the Weights and Biases alert feature. You can be notified via Slack or email if your Weights and Biases run has crashed or whether a custom trigger has been reached, such as your loss going to NaN or a step in your machine learning pipeline has completed. Weights and Biases alerts apply to all projects where your launch runs, including both personal and team projects. Get started with Weights and Biases alerts in two quick ways. Turn on alerts in your Weights and Biases user settings. You can get notified via Slack and or email for whether your run is finished, whether it has crashed, or any other custom trigger you like. For custom triggers, add 1db.alert to your code wherever you'd like to be alerted for a custom trigger. I've been told that Weights and Biases users love alerts and that some have saved large cloud GPU bills by being alerted early to crashed runs while training large, expensive models. So relatable. Try out Weights and Biases alerts now at 1db.me/AI coffee break. Great, let's go back to today's topic of comparing multi-head self-attention with convolutions. We got mixed signals about vision transformers during the last decades in machine learning. Whom are we kidding? VIT was published September 2020, which admittedly feels like a decade ago because of the insane pace of the field. If you want a quick recap about vision transformers, do check out our playlist about them. Here we make a recap on multi-head self-attention, or short MSA, and convolutions. The convolutional layer involves a kernel, basically a small matrix containing some numbers, that slides over the input and processes every region in the same manner. It's the same kernel values that get multiplied with the different values of the input. So the parameters are shared between image locations, inducing translation equivariance, since if we move the input across the image and we apply the same weights everywhere in the image, the output will remain the same but translate accordingly. Sharing parameters, so having the same parameters independently of the image region, is also a big plus if one wants to save memory. But then there's multi-head self-attention, or short MSA, that laughs at the whole concept of sharing parameters across the spatial dimension and instead dynamically computes a weight for each token. We remember the sequence spans across the spatial dimension. Let's break this down. We remember that 16 by 16 image patches are represented as vectors, or in other words, image tokens. To compute a new representation for this token here, attention scores are computed between this token and every other token in the sequence, including oneself. Then the representations of these image tokens are aggregated by a weighted sum in which the weight of each token is given by the attention score. So in this example here, this token contributes a lot for computing this new representation, this other token only very little. Of course, we do this for all tokens. So before, we had convolutions that compute a new representation for each pixel by taking the sum between all the pixels in a region weighted by the entries of the kernel. And now we have the self-attention layer, the result of which is a weighted average of all these image vectors that represent patches, like in convolutions. But now the weights of the sum are first positive and second, dynamically computed through this renowned formula here, where we remember that the data itself is considered here in the keys and queries. In other words, these attention scores are highly data dependent and not static like the kernel values of the convolution. Don't be confused. We are talking about inference here, or about one iteration during training. Of course, kernel values update during training so they can adapt to the data and the task at hand. When we say that convs are static, we mean that at one iteration or at inference time, they are fixed and do not depend on the data sample or spatial region in the data, while attention weights are computed for each data vector individually. Another difference between MSA and convs is that for MSAs, the weighted aggregation is done over the entire input. So unlike convolutions in CNN that are usually small windows like 3 by 3 and encompass a small spatial range in the image, self-attention encompasses a much longer range, the whole image. And why did we say that MSA laughs at the concept of saving memory? Well, while self-attention computes one score between each two image tokens, multi-head self-attention says, come on, why decide for only one set of scores if we can have 2 or 6 or 12? In this way, the network does not have to rely on one combination of attention scores, but on many of them that have the chance to specialize. This idea follows the motto that ensembling is in general beneficial in machine learning. In a similar manner, convolutional networks do not work with only one kernel per layer, but with more of them, where the weights can be adapted during training to specialize for specific features. Great, this was the short recap on MSAs versus convs, and we basically only explained the background of this little paragraph in the paper. So assuming we already know the key components of vision transformers, during the last 1.5 years in which we had time to study them, we still got quite a mixed signals about what is now exactly the difference between convs and MSAs. And this is what I love about this paper. It puts all of this together to get a more coherent picture about what exactly makes vision transformers great. The introduction of the paper reminds us of what we have been saying previously in our videos too. We think that the success of transformers in general and MSA in particular is due to two main reasons. First, the weak inductive bias of MSA. While convolutions have this parameter sharing property throughout the spatial dimension, MSA doesn't. So each image region can be handled by its own specific attention weights. Even more, these attention weights are data specific, as we discussed earlier. So there are more degrees of freedom when modeling with MSA than with convolutions, and the network has the chance to discover translation equivariance on its own, or even cooler properties if they are useful for minimizing the loss. And because there is less guidance from the start for the network, vision transformers are notorious to overfit on small datasets. It shall remain to be seen in this video whether this is true, but we know that techniques involving heavy data augmentation are needed for small data regimes, as we have seen with DEIT making VIT work on smaller datasets. The second reason is the extremely large context window of vanilla MSA that computes attention scores for each token based on every single other token. Attending to a wider context should lead to better performance, right? Right? Let's follow this paper-related work to see why this is not really the case. Modeling long-range dependencies does not necessarily result in higher performance. There are examples in the literature showing how a limited context window of MSA is beneficial on small and large datasets alike, like we have seen with the Swin transformer in one of our previous videos. And then there's these facts we should make sense of. Adding MSA to CNNs helps, especially when MSA is added closer to the last layer. And then we cite VITs are robust against data corruption and image occlusions, and especially against adversarial attacks where the attack consists of introducing high frequency noise. So what is it with MSA and the insensitivity to high frequencies now? Okay, hold your questions, because this paper is going to address them by hypothesizing that MSA is a trainable spatial smoothing of feature maps. And this makes sense when looking at the formula of self-attention. We take the image vectors or features across the spatial dimension and average them with importance weights that are all positive. So the authors go ahead and ask 3 questions. What properties of MSA do we need to better optimize neural networks? Do MSAs act like Convs? If not, how are they different? And third, how can we harmonize MSAs with Convs? Following the last question, they propose an architecture combining MSA and convolutions based on the lessons learned from answering the first 2 questions. Before going further into this, Ms. Coffee Bean wants me to make a small comment on how the authors arrived at their conclusions. The authors answered these questions by conducting their experiments on Sci-Far only. I mean, it is great that they compare different models like the ResNet, which is a ConvNet, and transformers like VIT, PIT, and SWIN. It's problematic again that they use the tiny versions of these models, but we have 2 questions. What about datasets other than Sci-Far, and how do the lessons of this paper generalize for tasks other than image classification, so for something like object detection or image segmentation? Keep this in mind throughout this video. Let's follow the paper and answer the first question. What properties of MSAs do we need to improve optimization? Well, the first lesson here is unsurprising. It seems like MSA is acting like a more generalized spatial pooling, generalized because it is trainable and data dependent. And this is a good inductive bias for image data. Only think about the data specificity. It's a nice thing to have, something we do not find in a data independent aggregation layer like we have in the MLP mixer. Nothing against the MLP mixer. It's really useful if we dislike the compute and memory footprint of MSA and are ready for a compromise in accuracy. The surprising bit is that due to the weaker inductive bias of MSA, the training of MSA-based neural networks is more difficult. They do not even overfit on small training datasets. We see here how 2 curves for training and test of VIT on Sci-Far 100 are very close to each other and are not exhibiting the gap specific to overfitting, not even in the small data regimes. Of course, this is also helped by the strong DEIT-like data augmentation the authors apply to VIT. Also interesting, but not surprising after we have learned about SWIN transformers and ConvNets, is that not the huge context window of MSA is the recipe to success, but a reduction of the degrees of freedom by limiting MSA to very small windows. We see in this picture how the lowest test error is achieved with a 3x3 window size for MSA. But Ms. Coffee Bean must comment again, because the authors conduct experiments on Sci-Far 100 where we would assume that long dependencies are not key for good performance. We expect this lesson to vary on more complex datasets and on tasks other than image recognition. Image recognition is too holistic for this, I guess. Describing the whole image with one label is not very challenging, and we would like to see results on other tasks like action recognition, where it is important to model how 2 different corners of the image interact with one another. But a cool thing to find out is that MSA comes with both advantages and disadvantages. On the bright side, MSAs flatten the loss landscapes. A flat landscape means better performance and generalization because, landing here or landing there on the lost landscape does not change much. In a less flat landscape, it means a lot if I land here or over there. But how do the authors know that the landscape is flatter for MSA? Well, they look at the eigenvalues of the Hessian matrix. Short reminder, the Hessian matrix of the loss function is a square matrix containing the second partial derivatives of the loss function. In English, please, we take 2 directions in our high-dimensional space that the loss function lives in and ask how does the change in one direction change with respect to the other direction. And the eigenvectors of this Hessian matrix are the principal directions of curvature. The eigenvalues speak about the magnitude of that curvature. A big Hessian eigenvalue speaks for high curvature, so for a very curvy and supposedly bumpy loss landscape. And guess what? MSA suppresses large Hessian eigenvalues, so This makes the loss landscape flatter for VIT, while the loss landscape of the ResNet has high Hessian eigenvalues, thus a higher curvature. This is a win for MSA. On the not so bright side for MSA, the authors read another thing from the Hessian of the loss function. Especially in the regimes of little data, a lot of Hessian eigenvalues turn out to be negative, so the loss landscape is non-convex for MSA. And if you hear non-convex, prepare for local minima that your optimizer might not escape from. But the good news is that more data also makes for less negative Hessian eigenvalues, so more convex losses. Given that in small data regimes the loss landscape is non-convex, it is again interesting to see that VIT does not overfit when training on small data sets. Local minima. So now, what is the difference between MSA and convolutions? First, something we have discussed already, convolutions are data agnostic and MSAs are data specific. Secondly, convolutions are channel specific, where kernels are learned for each channel. And MSA does not care on which channel they are applied. In fact, the patches that first consist of 3 channels for red, green and blue are all smashed together into one vector. So if we cite, convs are data agnostic and channel specific. In contrast, MSAs are data specific and channel agnostic. Then the conclusion of this paper is that they should be complementary. So we need them both. Nice. More interesting for Miss Coffee Bean is that MSAs are low-pass filters, but convs are high-pass filters. What does this mean now? A low-pass filter lets the low frequencies pass. So things like shape and white patterns in the image get through, while sharp details do not. Think about the low frequencies as the information that remains after blurring the image. Convolutions, on the other hand, are high-pass filters, meaning that they let high frequencies pass, like very fine edges in texture. Therefore, it is no wonder that, we cite, the results thus suggest that MSAs are shape-biased, where convs are texture-biased, which also confirms findings of previous work. The authors see these high-pass and low-pass characteristics by doing a Fourier decomposition of VIT and ResNet features respectively and comparing the resulting frequencies. Also, we are not surprised that CNNs, which are high-pass filters, not filtering out high frequencies, are vulnerable to high-frequency noise and adversarial attacks that introduce high frequencies into the image, so high that the human eye cannot even see. And the last difference we will discuss here between MSAs and convs is that MSAs average feature maps and reduce the variance of the feature maps in an ensembling-like effect. The authors support this by showing how MSAs rather reduce the variance and convs and MLPs increase the variance in their experiments. So it is no wonder that based on this, the authors move on to the third question of the paper of how can we harmonize MSAs with convs, and propose AlterNet, which in a nutshell is a ResNet with MSA blocks after each stage, especially at late stages to reduce feature map variance. We will let you decide what you think about this architecture after you find out about all its details. Honestly, due to the limited datasets, tasks and baselines explored in this paper, we are not very impressed by AlterNet, but we have seen with ConvNets that an enhanced ResNet can achieve good performance, so we do believe the author's message here that marrying convs with MSA seems like a good idea. If you want to know all the details that we missed or got wrong, read the paper. We have mixed feelings about its style. On the one hand, it has a good choice of words and flow of ideas, but it is also extremely dense and sometimes the required details are in unexpected places. Thanks for watching and sorry you had to wait for so long for this next video. PhD life is demanding and Miss Coffee Bean isn't animating herself.